Okay, it's recording now. I was saying we've shared some instructions about the report submission in the GitHub. You can see at the bottom part of the main GitHub document the report submission instructions. Deadline is July 12th. And you must submit a PDF document to my email, danny02@ucm.es, which contains the solutions to at least mandatory exercises. You can also include optional exercises, and they will be considered for the evaluation, but at least all the mandatory exercises. What to include as an answer to each exercise? Well, you can obviously you should include the code developed if the exercise asks for you to develop a code, but also explanations about the code that justify your work and that demonstrate that you understand what you're doing and you have done it yourselves. Also, you can include screenshots, photographs of the board, or even videos or links to videos, and any other relevant material that you consider important for justifying your answers. Okay. Any question about report submission? Okay, if you don't have questions, if you have questions later when you're doing your work before the deadline, let me know. You can send me questions to my email, or we can do a tutorship if necessary. Up to you. Okay, we're here for trying to help you doing the work. So Luis, I think you can start your presentation. Luis will be giving a talk for around 1 hour, and then, as usual, you'll have time to work, and we'll be here to answer your questions. Okay, thank you.
Thank you, Danny. Well, in this module, we bridge the gap between hardware and software by running a real-time operating system on the Beowulf SoC you've been working with throughout the course. One important point to keep in mind is that in real embedded systems, bare metal programming is the exception rather than the rule. Most production systems run an operating system, or RTOS, that provides hardware abstraction, multitasking, and a rich software ecosystem. This module gives you hands-on experience with that professional development model using Zephyr on RV-FPGA. First, I'll provide an overview of the Zephyr project RTOS based on the talk Zephyr Overview and Walkthrough by Benjamin Cabet, developer advocate of the Zephyr project. The goal is to give you a broad understanding of what Zephyr is, why it has become so important, what it can do, who is using it, and how well we'll use it. How we'll use it in the context of RV-FPGA. Zephyr has become one of the leading open source RTOSs for embedded system and is widely used on architectures such as RISC-V and ARM Cortex-M. Understanding its architecture, development tools, and ecosystem is a valuable skill for anyone pursuing a career in embedded systems. Let's start with what Zephyr is. Zephyr is a small, scalable, open source real-time operating system designed for embedded and resource-constrained devices. It is released under the Apache 2 license. which make it suitable for both open source and commercial products. One important point is that small doesn't mean limited. Zephyr can run on microcontrollers with only a few kilobytes of RAM, but it also scales to much more capable embedded systems. Another key feature of Zephyr is its governance. Zephyr is hosted by the Linux Foundation and developed under a vendor-neutral model. No single company controls the project. It is also important to remember that Zephyr is much more than just an RTOS kernel. It provides a complete embedded software platform, including networking, security, device drivers, file system, Bluetooth, USB support, and even machine learning frameworks. Finally, the Apache 2 license is one of the reasons Zephyr has been widely adopted in industry. It allows companies to build proprietary commercial products on top of Zephyr without being required to release their own applications source code. Let's take a quick look at the history of the Zephyr project. Zephyr began at Wind River Systems as an internal RTOS project called Rocket that was designed for small resource-constrained embedded devices. In 2016, Wind River open sourced the project, donated to the Linux Foundation, and renamed it Zephyr. From the beginning, it was released under the Apache 2 license to encourage broad commercial adoption. Over the next few years, the project grew rapidly as more companies joined the community. Today, Zephyr is supported by a large ecosystem of contributors from across the embedded industry, including companies on ARM, RISC-V, and many other hardware platforms. One of the reasons for Zephyr's success is its governance model. The Linux Foundation provides a neutral home where competing companies can collaborate on a common embedded software platform while contributing improvements back to the community. This slide gives a high-level overview of what Zephyr provides as an embedded software platform. As its core is the kernel, which provides services such as multitasking, scheduling, timers, memory management, and power management. On top of the kernel, Zephyr includes a wide range of connectivity and networking technologies, supporting everything from Bluetooth and Wi-Fi to Ethernet, USB, CAN, MQTT, HTTP, and secure communication protocols. Zephyr also places strong emphasis on security, which features such as secure boot, cryptographic libraries, and support for hardware security mechanisms. For developer, Zephyr provides a complete development environment, including West, Device Tree, Kconfig, CMake, and automated testing tools. Finally, it includes application frameworks such as POSIX API, login, command line shell, file systems, and graphical user interface libraries. The key takeaway is that Zephyr is much more than an RTOS kernel. It is a complete embedded software platform that provides most of the components needed to build a modern embedded application. This slide highlights the wide range of application domains that Zephyr supports. In the consumer space, Zephyr is used in products such as wearables, hearables, smart home devices, and many Bluetooth-enabled products. In industrial IoT, it powers smart sensors, industrial controllers, and building automation systems, where reliable real-time performance is essential. Zephyr is also gaining adoption in the medical and automotive sectors, where safety and reliability are critical requirements. Another rapidly growing area is Edge AI. Zephyr supports machine learning frameworks such as TensorFlow Lite Micro that allow AI inference to run directly on resource-constrained microcontroller. We'll see an example of this later in the labs. The key takeaway is that the same Zephyr application can often run on very different hardware platforms, including ARM and RISC-V, with only board-specific configuration changes. That's exactly the portability we'll take advantage of when running Zephyr on VirWolf. Zephyr is not just a research or hobbyist project. It is used in real commercial products. For example, Nordic Semiconductor NRF Connect SDK is built on Zephyr and powers millions of Bluetooth and cellular IoT devices. Zephyr is also used in industrial IoT, wireless modules, and other embedded products. The key takeaway is that learning Zephyr is very important, and you are learning a platform and development workflow that are widely used in professional embedded systems. I would like also to highlight one of the Zephyr biggest strengths, that is the extensive board support. As of version 2, it officially supports more than 700 boards. And once a board has been added to Zephyr, building an application for it is as simple as changing the board name in the West build command. In our course, VirWolf Nexus is one of those supported boards. Throughout the labs, we'll explore the device tree, kconfig, and support files that make VirWolf a Zephyr target. If you design your own board in the future, adding a board support to Zephyr follows exactly the same process that we are going to use on the labs. Zephyr includes drivers for more than 200 sensors, all accessible through a common sensor API. The advantage is that your application doesn't need to know the details of a particular sensor. Whether you are using a temperature, humidity, pressure, or motion sensor, you interact it with through the same API. This greatly improves portability. If you replace one supported sensor with another, the application often requires little or no modification. Although VirWolf doesn't include many onboard sensors, this is an important feature for anyone developing IoT or embedded products. One of the Zephyr's major strengths is its support for a wide range of processor architectures. As of version 4, it supports more than 12 CPU architectures, including ARM, RISC-V, x86, Xtensa, ARC, Spark, and others. For this course, the important one, obviously, is RISC-V. The Vir EH1 processor at the heart of VirWolf is a 32-bit RISC-V core, and Zephyr provides mature and actively maintained support for this architecture. The key takeaway is that the concepts you'll learn in this course are portable. Once you understand Zephyr on VirWolf, you'll be able to apply the same development model to many other hardware platforms supported by Zephyr. Well, so far we've looked at Zephyr from a high level. Now let's take a closer look at some of the key features that make it a powerful platform for embedded system. We'll focus on the features that are most relevant to our labs. This slide shows the high-level architecture of Zephyr, which is organized in two main layers. The first is the OS layer, which includes the platform-specific code, the kernel itself, and a rich set of services such as device drivers, networking, file system, Bluetooth, and cryptography. On top of that is the application layer where developers write their own code. Application access the hardware and operating system through Zephyr's API and through the optional POSIX compatibility layer. One important design decision is that by default, the kernel, drivers, and application all run the same address space. This keeps the system simple and efficient, which is ideal for resource-constrained embedded devices, but has some drawbacks. Zephyr also supports user space isolation on processors with a memory protection unit, but the Vir EH1 using VirWolf doesn't include one. So we'll use the simpler single address space model. Another key characteristic is that the kernel is highly configurable. Only the features required by the application are included, allowing Zephyr to scale from very small microcontroller to much more capable embedded systems. Device tree is one of the most important concepts in Zephyr because it separates the application from the underlying hardware. A device tree file describes the hardware on a board, its peripherals, memory map, pin assignment, and configuration. The drivers and the application then use this information instead of hard-coded addresses. In Zephyr, the SoC hardware is typically described in a DTSI file, while the board-specific details are added in a DTS file. If an application needs to customize the hardware description, it can do so with a device tree overlay without modifying the original board definition. We'll see this entirely in the VirWolf labs. The Blinky application simply uses the LED0 alias defining the device tree. It never knows which GPIO controller or pin is actually connected to the LED. If we change that alias in an overlay, the application will blink a different LED without changing a single line of C code. The example on the right shows a small fragment of a device tree source file. At the top, you can see the definition of I2C controller. It specifies properties such as the communication speed and the pins used for the I2C bus. Below are two devices connected to that bus, and LSM6 DSL inertial sensor and HTS 221 humidity and temperature sensor. Each device is identified by a compatible string, which tells Zephyr which driver to use, and a reg property, which gives its I2C address. The important point is that none of this information is hard-coded in the application or the driver. The hardware configuration is described in a device tree source file, and Zephyr uses that description at build time to configure the system automatically. West is Zephyr's meta tool, and it has three main roles. First, it manages the Zephyr workspace. It uses the West YAML manifest to download and keep all the required repositories synchronized, including the Zephyr kernel, the modules, and the BOA support packages. Second, it provides a simple interface for building application. Instead of invoking CMake and Ninja directly, we simply use West Build, and West orchestrates the complete build process. Finally, West provides an extensible command line interface. In addition to commands such as build, it also supports commands for flashing, debugging, testing, and project-specific extensions. In our virtual labs, we'll mainly use West Update to set up the workspace and West Build to compile the applications. One of the Zephyr's greatest strengths is its comprehensive connectivity support, which make it an excellent platform for IoT applications. It supports a wide range of communication technologies, including Ethernet, Bluetooth, Thread, LoRa, CAN, and many others, together with the corresponding networking protocols such as IPv4, IPv6, TCP, UDP, etc. On top of that, Zephyr provides built-in support for secure communication, cloud connectivity, such as MQTT, QoAP, HTTP, and over-the-air firmware updates, and also remote device management. In our virtual labs, we'll mainly use the UART interface, but the same Zephyr APIs can be used to add wireless networking and cloud connectivity if the hardware support those features. In addition to supporting many communication technologies, Zephyr also includes a complete networking stack. It provides native support for both IPv4 and IPv6, together with the standard internet protocols such as TCP and UDP. Application use the familiar BSD socket API, making easy to reuse networking code from Linux or other POSIX systems. On top of the networking stack, Zephyr support common IoT application protocols such as MQTT, QoAP, HTTP, WebSockets, as well as secure communication using TLS and DTLS. The key takeaway is that Zephyr provides everything needed to build connected embedded devices, from physical communication interface all the way up to cloud applications. Sorry. Power management is essential for battery power embedded devices, and Zephyr includes a flexible framework to reduce energy consumption while keeping the system responsive. The kernel uses a tickless scheduler, so when there is no work to do, it can replace the processor. It can place the processor into a low power state instead of waking it periodically. Zephyr also provides system power management, which control the processor's sleep states, and also provides device power management, which allows individual peripherals to be suspended or resumed as needed. Most of this functionality is handled automatically by the kernel. On VirWolf, power management is limited, but the same Zephyr framework scales to low power IoT devices, which with much more advanced sleep modes. Zephyr includes a major USB stack with support for USB 2, USB-C, and the most common USB device classes, including virtual serial ports, mass storage, AHD devices, and firmware updates. Although we won't use USB in this course, it is another example of how Zephyr provides complete software stacks for modern embedded systems. Security is a key part of the Zephyr ecosystem. Zephyr uses MCU boot as its secure bootloader, allowing firmware to be signed and verified before they are executed. It also supports secure over-the-air firmware updates, enabling devices to be updated remotely without physical access. Although we'll program Beowulf through JTAG in the labs, production IoT devices typically rely on secure boot and OTA updates. In addition to secure boot, Zephyr provides a comprehensive security framework. It includes cryptographic APIs for encryption, hashing, and random number generation. Obviously, it can take advantage of hardware security features when they are available in the hardware. Zephyr also integrates with trusted firmware to support secure key management, firmware verification, and device authentication. Although Beowulf doesn't include these hardware security features, the same Zephyr APIs can be used on more capable platforms. Zephyr provides a POSIX compatibility layer, making it easier to reuse existing Linux and POSIX application on embedded devices. It also supports running Zephyr application as native Linux programs, which simplifies development, debugging, and testing before deploying to the target hardware. We'll see an example of POSIX API in the Beowulf Labs, where they provide a familiar programming model for application development. Real time. At its core, Zephyr is a real-time operating system, so efficient scheduling is one of its most important features. The benchmark on this slide show that common kernel operations, such as creating threads, switching between them, and synchronizing with semaphores, take only a few microseconds. Zephyr supports both preemptive and cooperative scheduling, allowing multiple tasks to run efficiently while providing predictable real-time behavior. We'll see in the practice in the Blinky lab where KM Sleep allows the scheduler to run other threads instead of wasting CPU time in a busy wait loop. Zephyr also supports graphical user interfaces through its integration with LVGL, one of the most popular open source graphical user interfaces libraries for embedded system. It includes drivers for many types of displays, such as LCD, touch screen, e-ink display, which make it suitable for a wide range of embedded application. Although we won't use graphical displays in the Beowulf Labs, this is another example, one more, of how Zephyr provides a complete software platform for modern embedded platforms. Zephyr provides several built-in mechanisms for communication between threads. Depending on the application, you can use message queues, mailboxes, pipes, FIFOs, and other kernel services to exchange data safely and efficiently. Zephyr also includes ZBus, a publish-subscribe message bus that allows one component to publish data while multiple components subscribe to it. This makes it easier to build modular and loosely coupled applications. Although we won't use this mechanism in our labs, they are essential for developing larger embedded systems with multiple concurrent tasks. Zephyr provides powerful logging and tracing tools to help developers understand and debug embedded applications. The logging framework supports multiple output backends, such as UART and network interfaces with configurable log levels. The tracing framework records kernel events uh, mainly, making it possible to visualize thread execution, interrupts, and synchronization. And this is especially useful when debugging real-time systems. In our labs, we'll mainly use the logging framework over UART to observe the application's behavior. One of the Zephyr's strengths is that it is governed by the Linux Foundation under a vendor-neutral model. This means no single company controls the project. Instead, technical decisions are made collaboratively, and maintainers and contributors from across the embedded industry can participate. This governance model, together with regular releases and long-term supervision, give companies confidence to use Zephyr in commercial products. The key takeaway is that Zephyr is not just an open source project. It is an industry-wide collaboration uh, backed by many of the major players in the embedded system. These are some of the platinum members of the Zephyr project. The list, sorry. The list includes major semiconductor vendors, technologies, companies, and industrial manufacturers such as Intel, Nordic Semiconductor, NXP, Qualcomm, Google, Meta, and Analog Devices. The key takeaway is that Zephyr has a strong backing from across the embedded industry. These are some of the silver members of the Zephyr project. They include semiconductor vendors, software companies, tool providers, and system integrators from across the embedded industry. The diversity of this list shows that Zephyr has become a broad industry platform. The key takeaway is that Zephyr has a strong ecosystem and is widely adopted across many hardware platforms and applications domains. Zephyr is much more than an operating system. It has a complete ecosystem built around it. The ecosystem includes development tools, middleware, firmware, training, consulting, and large community of contributors working under the Linux Foundation. The key takeaway is that Zephyr is a mature and growing platform. Zephyr is supported by a rich ecosystem of development tools. Developer can use popular IDEs such as Visual Studio Code and Eclipse, standard compiler toolchains, and professional debugging tools such as OpenOCD or Seger JLink. Zephyr also integrates with simulation and emulation platforms such as Renaud and Webkey that allow applications to be developed and tested even without physical hardware. As Zephyr has grown, so as is ecosystem of training and consulting. Today, official training is available through the Zephyr project and the Linux Foundation, while many semiconductor vendors and embedded companies also provide courses and technical support. The existence of this ecosystem reflects Zephyr maturity and its widespread adoption in commercial embedded systems. Zephyr integrates with a wide range of open source firmware libraries and middleware. These include security libraries, networking stacks, file system, graphical user interface libraries, and TinyML frameworks such as TensorFlow Lite Micro. The key advantage of these components are managed uh, the key advantage is that these components are managed as Zephyr modules. West automatically download and integrates them, so developers can enable the functionality they need without manually adding external libraries. In our lab, we are going to use TensorFlow Lite Micro to demonstrate AI inference on the Beowulf platform. Zephyr also integrates with high-level application frameworks and cloud platforms. These services provide capabilities such as remote device management, monitoring, logging, and over-the-air firmware updates. The key takeaway is that Zephyr doesn't stop at the operating system. It provides the building blocks needed to develop and manage complete connected embedded applications. Before moving to the labs, it's useful to understand where Zephyr fits in the embedded software landscape. Zephyr targets the same class of devices as RTOSs such as FreeRTOS and ThreadX. That is resource-constrained microcontrollers and SoC. Its main differentiators are its rich feature set, broad hardware support, and a strong open source governance. The key takeaway is that Zephyr has become one of the leading choices for new embedded design when Linux is too heavyweight, but a modern full-feature RTOS is required. In the next few slides, we look at some of data that illustrate Zephyr's growth, adoption, and position within the embedded software ecosystem. This table compares Zephyr with some of the most widely used RTOSs. FreeRTOS remains the most widely deployed RTOS and is often chosen for simple embedded application, while ThreadX has a strong presence in commercial and safety critical systems. Zephyr distinguishes itself through its vendor-neutral governance, extensive BOA support, integrated networking, and security. These features make it possible to build complete connected embedded system using a single software platform. The trade-off is a steeper learning curve, but that complexity comes from the breadth of functionality Zephyr provides. As we see throughout this presentation, it offers far more than just a real-time kernel. This chart compares the average number of contributors across several open source RTOS projects. Zephyr stands out with steady growth and a much larger contributor community than the other projects shown. The key takeaway is that Zephyr is one of the most active open source RTOSs today. This chart shows the average number of commits per month across several open source RTOSs projects. Once again, Zephyr stands out with a much higher development activity than the other projects. This reflects a large active community continuously adding features, supporting new hardware, and fixing bugs. The key takeaway is that Zephyr is not only growing in contributors, but also in the pace of its development. This slide highlights three important trends shaping the future of Zephyr. The first is the combination of RISC-V and AI/ML, where Zephyr is becoming a key platform for running machine learning on low-power embedded devices. We'll see this directly in our labs with the TensorFlow Lite Micro example on Beowulf. The second is the continued growth of IoT and edge computing. Finally, Zephyr is expanding into safety critical applications with ongoing work toward industry certifications for automotive and industrial systems. Together, these trends show why Zephyr is attracting increasing interest from both industry and the open source community. We're now seeing what Zephyr is, what it offers, and why it has become such an important platform for an embedded system. The next step is getting started. In the following slides, I'll point you to the main sources for learning Zephyr, and then show how we apply them in the RV FPGA labs. As with any new framework, the best way to learn is by building and experimenting. And that's exactly the approach we'll follow in this module. If you are getting started with Zephyr, the official Getting Started guide is the best place to begin. It walks through you through setting up the development and building your first application. From there, explore the hundreds of sample applications included with Zephyr. They are an excellent way to learn different subsystems by example. The device tree bindings documentation is another valuable reference, especially when working with new hardware. And if your hardware isn't already supported, don't be discouraged. Zephyr driver model is well documented, and very often you can start by adapting an existing driver rather than writing one from scratch. This slide summarizes the main resources available to the Zephyr community. The official website and documentation should always be your first reference. GitHub repository provides the source code, release notes, and hundreds of sample applications. If you need help, the Zephyr community is very active through Discord, GitHub discussions, and mailing list. For this course, the labs handout contain everything you need to get started, together with links to the relevant Zephyr documentation whenever additional information is required. We now move to the from the general overview to its use on the VirWolf SoC. This is where concepts we've discussed become concrete. VirWolf is a real production quality SoC, and its Zephyr module provides the board support needed to run Zephyr just like any other supported platform. Throughout the labs, you'll use the same concept we've covered today to build and run application. You'll even explore a TensorFlow Lite micro example, showing how Zephyr can support AI workloads on embedded RISC-V systems. These labs follow the same workflow used by embedded engineers when bringing up a new hardware and developing applications on Zephyr. Before we start the labs, let's introduce the hardware and software platform we'll be using. As you already know, VFPGA is based on the VirWolf SoC. VirWolf is a FuseSoC based reference platform and is built around the CHIPS Alliance Vir EH1 RISC-V core. VirWolf can run the Zephyr project through its dedicated Zephyr module. I should point out that the current module targets Zephyr 2.7.4, which is an older long-term support release. Obviously, updating the port to a newer Zephyr release will be an excellent contribution to the project and an optional task. The platform can be used either in Verilator simulation or on a physical Nexus A7 FPGA board. The hands-on labs consist of 3 labs that progressively introduce Zephyr on VirWolf. Lab 1 is about getting everything running. You'll install VirWolf, install Zephyr and the SDK, run the provided examples, build your own applications, and execute them both in simulation and on the Nexus A7 FPGA board. The lab finishes with a TensorFlow Lite micro example. Lab 2 focuses on understanding how a Zephyr application works. We'll trace the Blinky sample from the device tree through the GPIO API down to the VirWolf GPIO driver. You'll also see how Zephyr's scheduler works through the KMS lib. And the exercise is to modify the application so that all 16 LEDs blink sequentially. Lab 3 looks at the Zephyr support itself. We'll examine the board definition, kconfig files, device tree files, the GPIO driver, and the SoC initialization code. Then you'll make your own modification by creating a device tree overlay and, as an advanced exercise, optional obviously, extending the GPIO driver to support the board switches. Taking together, these 3 labs take you from simply using Zephyr to understanding how applications interact with the operating system and to understanding how hardware support is implemented. The final exercise is representative of the kind of work involving importing a new board or SoC to Zephyr. This slide explains the architecture behind the setup process. The lab handout contains all the commands, so here we'll focus on the concepts. First, West manage the software workspace. The West YAML manifest defines the Zephyr kernel, the VirWolf module, and the other repositories needed for the project. Running West update fetches everything and keeps the workspace consistent. Next, FuseSock manages the hardware side. It handles the HDL sources that make up the VirWolf's SoC and provides the simulation and FPGA build flows. Finally, the build chains start with West build and West orchestrates the process. CMake configures the project, kconfig select the enable features, and Ninja invokes the RISC-V cross-compiler. The result is a RISC-V executable that can be run either in simulation or on the FPGA board. This slide shows the complete flow from writing Zephyr application to running it on VirWolf. The first key concept is board abstraction through device tree. Your application never accesses hardware register directly. Instead, it uses Zephyr API. For example, the Blinky application simply uses the LED 0 alias, and at build time, the device tree resolves that alias to the correct GPIO controller and pin for the selected board. This means that the same application can run on different hardware simply by selecting a different board during the build without changing the application code. The second concept is that there are 2 development paths for the same application. During development, Verilator Simulator provides fast iteration without requiring hardware. Once the application is working, you can run the same program on the Nexus A7 FPGA board. The only difference is how the program is loaded. For simulation, the executable is
convert it into a hexadecimal memory image that initialize the simulated memory. And for the FPGA, the executable is uploaded to the board over JTAG using OpenOCD. In both cases, the same application binary is executed. This slide introduces WEST, which plays two important roles throughout the labs. First, WEST is a repository manager. It uses the WEST YAML manifest to define which repositories make up the workspace and synchronize them. In our case, that manifest is provided by the VirWolf project. Running WEST update automatically downloads Zephyr, its modules, and all the required dependencies, creating a complete and consistent workspace. Second, WEST is the main command line tool for Zephyr development. We will use it to build application, and it can also be used to flash, debug, and test Zephyr projects through a common interface. You will also notice the .west directory at the root of the workspace. This directory stores West local configuration and identifies the workspace root. In the labs, the workspace is created just with three commands: West init, West config, and West update. After that, the Zephyr environment is ready for development. This slide introduces the three main concepts you will explore in the Blinky lab. The first is device tree aliases. The application doesn't know anything about the underlying hardware. It simply refers to LED 0, and at build time, Zephyr resolves that alias to the correct GPIO controller and pin for the selected board. This is what makes the same application portable across different hardware platforms. In the lab, you will inspect the VirWolf Nexus DTS file to see where that mapping is defined. The second concept is the GPIO API. The application uses standard Zephyr API calls to configure a GPIO pin and change its state. Those calls are dispatched to the VirWolf GPIO driver, which automatically access the memory map GPIO registers. In the next lab, you will trace this entire software stack from the application down to the hardware. The third concept is KM-Sleep. This is your first example of the RTOS scheduler in action. Instead of wasting CPU timing in a busy await loop, the thread goes to sleep, allowing other threads to run. That's one of the key advantages of using RTOS instead of bare metal programming. As you work through the lab, think about this question: what would happen if the KM-Sleep were replaced in a busy wait loop while another thread was running at the same time? This slide introduces the structure of the VirWolf Zephyr module. The file tree is included in the lab handout. So here I will focus only on the role of each directory. The key idea is that this module is a complete Zephyr board port. The same structure is used whenever a new board or SoC is added to Zephyr. By understanding this module, you will understand how Zephyr supports new hardware. The boards directory contains the board definition. In particular, the device tree describes the board hardware, GPIOs, UART, LEDs, and aliases such as LED 0. While the kconfig make the board visible to the build system. The drivers directory contains the VirWolf GPIO driver. This is the layer that translates the generic Zephyr GPIO API into the hardware-specific register accesses required by the VirWolf GPIO peripheral. The DTS directory separates SOC information from board information. The DTSI file describes the common Vir EH1 hardware, while the board DTS file adds board-specific components such as LED and other peripherals. Finally, the SOC directory contains the low-level initialization code that prepares the processor before the Zephyr kernel starts running. Well, as you work through the lab, try to follow one complete software path from the GPIO pin set in the Blink application through the Zephyr GPIO API into the VirWolf driver and finally to the hardware register. Data abstraction stack is one of the most important concepts you will learn in this module. Now, let's move on the hands-on lab. To save time, Daniel sent you the lab instruction a few days ago, and we asked you to install the VirWolf and Zephyr before today's session. If you haven't done that yet, please start with the installation. It typically takes more than 20 minutes. Once your environment is ready, complete the smoke test by running Zephyr both in simulation and of the FPGA board. And after that, you can continue with the remaining labs. If you need any help during the session, don't hesitate to ask me. And if more detailed assistance is needed, I'll start a parallel Google Meet session so we can troubleshoot your setup without interrupting the rest of the class.
Thank you, Luis.
Any question?
Thank you, Luis, for the presentation. I wanted to ask, these slides are available in the GitHub?
Yeah, I think so.
I'm not sure. Maybe we haven't shared that.
Maybe there is an old version, but I can put it in on the GitHub.
Okay, thanks.
Have you already set up the environment?
No, not yet. I'm doing it now.
Okay.
Yeah, same here, doing it now.
I'll stop recording now.